Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. We'll continue discussing some more mathematical preliminaries associated with a matrix A, pertaining especially to its spectral properties. So let's restart with a quick recap of what is a Jordan normal form. Let us consider any squared matrix A and let its eigenvalues be lambda I and the corresponding eigenvectors be Vi. Then the Jordan normal form associated with the matrix A is given using this relation J equals S inverse of AS, where the matrix S simply consists of the eigenvectors as all of its columns, meaning this. So we discussed in the previous lecture that the structure of the matrix J, whether it's diagonal or not, depends completely on the nature of its eigenvalues and the associated eigenvectors. So let us start with a matrix A, all of whose eigenvalues are completely distinct. And let's try to see what are the properties associated with such a matrix. Now the first result that we have here says that if we have such a matrix A, whose eigenvalues are distinct, then the corresponding eigenvectors are always going to be linearly independent. Let's see a quick proof of this. We begin by considering the simple case of n equals 2, meaning the dimension of n is 2, meaning we have two eigenvectors v1 and v2. Now, let us try to do the proof by contradiction, meaning we assume that v1 and v2 are actually linearly dependent, which would imply that if we are to solve this expression, note that v1 and v2 are eigenvectors to begin with, so both of them are not equal to 0. Then if we are to solve this equation, we will have as the solution, which implies that actually C1 v1 is simply equal to minus of C2 v2. Okay. So again, let's start with the first relation. And multiply and left multiply A. So here this 0 is simply a column vector. So of course, we can do some rearrangements very easily given by this. And since v1 is the eigenvector, we can always express it in this manner. Meaning this becomes C2 v2. But what do we have from here? We know that C2 v2 is simply minus of C1 v1. So now let me substitute that here. This gives, I can take C1 and C2 common, and lambda 1 minus lambda 2 equals 0. What do we know? We know that C1 and C2 are not equal to 0. We know that V1 and V2 are not equal to 0. And we also know that the eigenvalues are distinct, meaning lambda 1 is clearly not equal to lambda 2, which implies that lambda 1 minus lambda 2 is certainly not equal to 0. But what do we get from here? Since the first two terms are not equal to 0, the only way this equation can hold is when this difference is equal to 0, which means lambda 1 has to be equal to lambda 2, which is a contradiction as the eigenvalues of A are supposed to be distinct. Since we have a contradiction, which means our assumption of v1 and v2 being linearly dependent is actually wrong, meaning whenever we have two eigenvalues which are distinct, the associated eigenvectors are always linearly dependent. And this derivation can in a similar manner be extended to larger dimensions as well. Now, moving further with the results. So, we showed that the eigenvectors associated with distinct eigenvalues are linearly independent. Now, let us try to do some more rearrangement and see if we get more nice properties. We start with the matrix S, which, to remind you, consists of all of the eigenvectors as its columns. Now, let us left multiply A to it. So, then as you can see, it simply gets multiplied by each of the columns here, meaning it can be simplified in this manner. So, what is AV1? So, since V1 is nothing but an eigenvector, we can substitute here lambda 1 V1. Similarly, this becomes lambda 2 V2 and lambda n Vn. So, what do we have here? The matrix AS is simply equal to this matrix. Now, any matrix expressed in this form can be written as a product of two matrices. So, let's see, since we have skipped a step here, let's see this a little bit. Suppose we have any matrix A whose vectors are simply equal to meaning the matrix is actually equal to let us erase this so that it is clear. Then we can always take 3 and 5 out here. If you do the multiplication now, you see that this is exactly the same as this, which is how we get this relation. Remember, this is a matrix S, and this is simply the matrix consisting of all of the eigenvalues along the diagonal, and rest all of the entries are equal to 0. This is a Jordan matrix. So, now let us left multiply S inverse on both the sides. So, S inverse and S when multiplied together simply becomes equal to identity, and what remains is the Jordan matrix here, meaning J is simply given by S inverse AS. And what do we observe here? We already knew this relation, but the interesting thing that we observe here is that whenever the eigenvectors of A are distinct, the Jordan matrix is always a diagonal matrix, and the diagonal entries are nothing but the eigenvalues of the matrix. So, here is a quick example of it. Suppose we start with this matrix A, then we calculate the characteristic polynomial, which gives us the eigenvalues 1 and 3, and the associated eigenvectors are 1 0 and 4 1. So, see, since the eigenvalues are actually distinct, we know that a Jordan matrix is supposed to be diagonal. So, if we do the calculation of S inverse AS, then we observe that we get a Jordan matrix which is actually not only diagonal, but the diagonal entries consist of the eigenvalues as discussed in the previous result. Now, let us look at the case when the matrix A does not have distinct eigenvalues, but has repeated eigenvalues. So, how do we calculate the Jordan matrix in that form is the first question. The second question is, does the Jordan matrix now remain diagonal or not? So, in our previous definitions, we already saw that when the algebraic multiplicity of an eigenvalue is equal to 1, it is known as simple, and whenever the algebraic multiplicity is greater than 1, meaning it is a repeated root, then the eigenvalue is also said to be a repeated eigenvalue. Now, whenever a matrix has repeated eigenvalue, certain times it does not really have enough independent eigenvectors. So, in that case, how do we construct the matrix S? S is supposed to have n columns. But when the eigenvalue is repeated, then sometimes we do not really have n number of eigenvectors. So what do we do then? So we'll answer this question in a short amount of time. Let's quickly see an example. Let us consider this matrix. This is a very simple matrix whose eigenvalues are equal to. So since this is in a block triangular form, it's very easy to calculate the eigenvalues. So we know that simply 1, 1, meaning 1 is a repeated eigenvalue whose algebraic multiplicity is equal to 2. Let's try to calculate the eigenvector here. So I'll split it into components. What do we get here? V2 equals 0 is the only solution here, and the other equation is simply this. So meaning the span, so let's see what is eigenspace here, mean the set of all feasible eigenvalues or the eigenspace is simply given by the span of this. Okay. So what do we see here? We see that we had two eigenvalues, both with values 1. But how many eigenvectors did we get here associated with it? Only one, which is equal to this. So we just pick one element from the span, let's say this. So we got only one eigenvector associated with it. Then what do we do? How do we construct the matrix S? We are supposed to have two eigenvectors. So S should be invertible, so that is why we need all of the eigenvectors to actually be linearly independent. So, but we do not get that, we get only one eigenvector. How do we go ahead and calculate the rest? Let's answer that question. In order to be able to do that, we construct what are known as generalized eigenvectors. Now, any vector V is known as a generalized eigenvector of grade n if it satisfies two properties. The first is a minus lambda I raised to the power n times V should be equal to 0. The second is a minus lambda I when raised to the power n minus 1 multiplied with V again should not be equal to 0. Now, these are the two properties which a generalized eigenvector of grade n must satisfy. Obviously, for the case when algebraic multiplicity is equal to 1, then we have n equals 1 here, which just leads us to the ordinary eigenvector. So, please note that any eigenvector which is calculated using this formula is simply referred to as an eigenvector or an ordinary eigenvector. So, we will keep referring to an eigenvector being ordinary or generalized. Generalized if it satisfies this property, and if it is calculated using this rule, it becomes an ordinary eigenvector. So, let us see how do we actually calculate the generalized eigenvector. To do that, let us start with some vector Vn and we set it to some value V. Then the generalized eigenvectors actually form a chain which goes in this manner. If Vn is equal to some V, then Vn minus 1 is simply calculated by setting it being equal to a minus lambda I times Vn. Similarly, Vn minus 2 is actually equal to a minus lambda I times Vn minus 1. We keep on repeating this process. We reach V1. V1 is simply equal to A minus lambda I times V2. So this is what gives us a chain of generalized eigenvector. So notice that we need something. If we know just one of the vectors here, we can calculate the rest. So let's start with the vector V1. If you notice here, the vector V1 is simply the ordinary eigenvector. Then this is how it goes. So let's see. Let's do the calculations, everything in terms of V1. So since V1 is an ordinary eigenvector, we know that this property holds, okay, which simply gives us back the standard relation A V1 equals lambda V1, which proves it further that it is the ordinary eigenvector. Then let's come to calculate the second generalized eigenvector, which is V2. How do we go ahead with that? So we know the relation that V1 is simply equal to A minus lambda I times V2. So this gives the relation. Which can be simplified to AV2 being equal to V1 plus lambda V2. Similarly, AV3 is given by V2 plus lambda V3. Similarly, AVN is actually given by Vn minus 1 plus lambda Vn. Okay. So how does this help us in calculating the Jordan blocks? Let's see that. So in order to understand that, let us start with a simple case of n equals 2 and see how it goes. When n is equal to 2, V1 is a standard ordinary eigenvector, and we know that from here, we know that AV2 is actually equal to V1 plus lambda V2. Now what does this mean? Let's see. So we have this relation AS, where S is nothing but V1, V2. So now we have two eigenvectors V1, V2. So let's see, what is AV1? It is nothing but lambda V1. And what is AV2? If you observe here, AV2 is simply equal to, you see, so we see that through some simple calculations, what we can do is, we can represent this matrix can be represented as a product of these two matrices here. Sorry, this is S. So what do we have here? We see that, let's again we have this relation if we left multiply S inverse, so we get is simply equal to S inverse AX. So what do we see here? We observe that the Jordan block is now, the Jordan matrix is no more diagonal in nature. The superdiagonal element here actually has a non-zero entry which is equal to 1. So if we repeat this process for larger matrices, then we get this neat form. Now, so this, notice that we are now calling it Jordan block. Why do we call it a Jordan block? Because it simply pertains to the eigenvalue lambda. In the case of repeated eigenvalues where we are not able to compute n number of, or let's say if the eigenvalue is repeated k times, and we are not able to calculate k number of linearly independent eigenvectors, then we go on to compute the generalized eigenvectors, which leads to a Jordan matrix where the diagonal entries again are nothing but the eigenvalues lambda, and the super diagonal element here is always equal to 1. So, this is what happens when the matrix has an eigenvalue which is repeated such that we are unable to find enough number of linearly independent eigenvectors. Such matrices where the Jordan block does not remain diagonal anymore have a special name. They are said to be defective matrices. Notice further here that the geometric multiplicity, which is simply the number of linearly independent eigenvectors that we can find, is equal to 1, and the algebraic multiplicity is simply the number of times it is repeated, which is equal to k. Meaning, for such matrices and for that particular eigenvalue, we have the algebraic multiplicity not equal to the geometric multiplicity. So, this is the property of a defective matrix. In every defective matrix, the eigenvalue for which is repeated and satisfies this property A is not equal to Gm, we will always have such a Jordan matrix. So, this is a quick example of it. So, we take this matrix A, again we calculate its characteristic polynomial. We see that the eigenvalue lambda is actually repeated thrice, and when we go on to calculate the eigenvector, so we will realize that we have only one eigenvector which we can find, meaning the eigenspace has dimension 1. In that case, we cannot do the Jordan decomposition because we are falling short of 2 linearly independent eigenvectors. So, what do? We go on to calculate the generalized eigenvectors. So, the first step shows the process of calculating the ordinary eigenvector, which, as we wrote here, is equal to the vector containing all ones. Then we try to calculate the second eigenvector V2, which is now a generalized eigenvector. We know that it satisfies this property. Through some algebra, we get this as a suitable value of V2. We repeat the similar process for V3 and get another eigenvector V3. So, now, I leave this task as students to verify. Suppose we now go ahead to calculate S inverse AS, where what is S? Again, it consists of this. The student should now see whether or not they get this property. The super diagonal should have all ones, and this should consist of all of the eigenvalues, which is 3. Okay. And all of the other entries are simply 0. Okay. So, now we know, given any matrix A, how we can actually calculate its Jordan form, and we also know that Jordan form is generally of 2 types. The first is a diagonal Jordan form. Now, in a diagonal Jordan form, there can be 2 possibilities. There could be some eigenvalues which are even repeated. Now, in a repeated eigenvalue where the Jordan matrix is diagonal, the algebraic multiplicity must be equal to the geometric multiplicity, meaning we should be able to find enough number of linearly independent eigenvectors associated with that eigenvalue. An example which we discussed before was this matrix, which actually has geometric multiplicity and algebraic multiplicity the same. In this case as well, so this itself is its Jordan form. This is exactly what we will get. Now, in these cases also, our Jordan matrix is actually diagonal. This is the Jordan matrix. But whenever AM is not equal to GM for an eigenvalue, then we always get a Jordan matrix which takes this particular form. The diagonal has the repeated eigenvalue, the super diagonal has all ones, and rest of the entries, so this is all ones, and rest of the entries are all zeros. Now, in terms of the Jordan blocks as well, we can redefine some of the notions which we discussed before. So, let us see. What is a geometric multiplicity? The geometric multiplicity, as before, is simply the number of linearly independent eigenvectors associated with an eigenvalue lambda, or it is also equal to the number of Jordan blocks associated with an eigenvalue. For example, let us see a case. Suppose we have some matrix A which has lambda as a repeated eigenvalue. Then what we can get is something like this, even. Suppose this is the Jordan block and not the entire Jordan matrix. And say the rest, all the entries are 0. So, now let us see. What is the algebraic multiplicity of the eigenvalue? It is simply the sum of all of the eigenvalues that are associated with it. So, what is the algebraic multiplicity of the eigenvalue lambda? It is simply equal to the sum of the sizes of all the Jordan blocks that are associated. The first Jordan block that is associated has a size 3. The second one has a size, so this is 3 cross 3, this is 2 cross 2, and here this is, it can be written as this. In that case, the algebraic multiplicity is simply equal to, meaning 7. And what is the geometric multiplicity? It is simply equal to the number of Jordan blocks that are associated with an eigenvalue, meaning, so we have one Jordan block here, another Jordan block here, and here if you see we have 2 more, each of size 1. In this case, it is simply equal to 1, 2, 3 and 4. 4 Jordan blocks are associated. Okay. So, this is how we calculate the algebraic and geometric multiplicities from the Jordan matrix. Again, what is simple eigenvalue? A simple eigenvalue is simply when the algebraic and geometric multiplicities are equal to 1. In other words, the Jordan block here will always have a size 1. What is a semi-simple eigenvalue? Now, all of its Jordan blocks have to have a size 1 and the eigenvalue should be a repeated eigenvalue. Again, an example is this case. So, if you see here, this is one Jordan block and this is another Jordan block. In this case, we can always find like the eigenspace has a dimension of 2. So, in such cases, the geometric and algebraic multiplicity, as we can see here, are both equal, in this particular case equal to 2. So, this brings us to an end on the discussion on the spectral properties associated with a matrix A and its Jordan matrix. So, the properties of Jordan matrix are extremely useful in calculating the emergent behaviors of the system. So, the next lecture will introduce some more mathematical preliminaries And then towards the end of it, we'll try to see the DeGroote model, which we discussed at the start of the lecture today. How do we actually use these mathematical preliminaries, especially the Jordan forms, and then more of the spectral properties. We'll put these together and see how exactly the discussion will go. Will the agents achieve consensus, or is the matrix associated with the system, is it going to diverge or not? So we'll try to arrive at all these conclusions in the next lecture. Thank you.